I see. MTL has a
Okay, we should be live now. Hello, everyone. This is the first day of iQuHACK 2022. And we're really excited to start off with some tutorials, the first of which will be given by QuTech. A little bit about QuTech. QuTech was founded in 2014 as a collaboration between Delft University of Technology, TU Delft, and the Netherlands Organization for Applied Scientific Research, TNO. It is positioned as a separate research institute within the TU Delft organization. And at QuTech, they work on a radically new technology with world-changing potential, quantum computing. Our mission and their mission is to develop scalable prototypes of a quantum computer and inherently safe quantum internet based on the fundamental laws of quantum mechanics. And I'm just going to hand it right away to Richard, who will be giving the first of 3 mini tutorials. So yeah, go right ahead.
Okay, well, thank you, Shantanu. Welcome, everybody. Great to, well, not actually see everybody, but I'm happy that everybody's here, and I'm really excited that this hackathon is starting. This is the first time that QuTech will be participating in this hackathon, and I'll tell you just a little bit about QuTech, and then go on to some more technical details about our platforms. I'll be giving this talk together with 2 of my colleagues, Tumi and Miguel, who will take over after me. So, like Shantanu already said, our mission is to develop scalable prototypes of a quantum computer and a very safe quantum internet based on, of course, quantum mechanics. And our institute QuTech consists of 3 departments. We have a quantum computing department, a quantum communication department, and a qubit research department. And we have a lot of PhDs and postdoc students working with us through the University of Delft, and a large number of TNO engineers who together try to make this mission possible. And one of the things that we started doing a couple of years ago is to build quantum demonstrators. And we call them demonstrators or sometimes prototypes, because we understand that we're still a long way from building actual quantum computers that are useful and yield, let's say, economic advantage to users. But our goal is to make quantum technology accessible to a wider audience and future users. And I think you're all part of that audience. So what do we want to do? We want to educate users on how to use quantum technology and how to get the best out of quantum technology. We build full stack demonstrators because we want to test the interoperability between the different components. Some of the components are developed in-house. Some of the components we develop together with some other companies in our ecosystem. And we want to develop new applications and products and services for the world. And of course, all of this is actually meant in the end to generate the required market pool, because at one point in time, this whole technology should become a commercial product for the users, but that's not our main goal. So we're not here to produce commercial products. We're here to, let's say, do the intermediate step and bring the technology to the market. Currently, we have 2 demonstrators. We have a quantum computing demonstrator, which is Quantum Inspire. This is a cloud quantum computing platform, and we have a quantum internet demonstrator, the Quantum Network Explorer. And we'll tell you a little bit more about Quantum Inspire. So we started with Quantum Inspire in around 2018. In the end of 2018, beginning of 2019, we put the platform online for a limited number of users, and mainly focused around our emulator. So it was mainly to test our cloud environment and to see if we could do cloud quantum computing on an emulator. But in 2020, we put a full system online, which was actually the first quantum computer in the cloud in Europe, but it was also the first one in the world to contain both a processor of spin qubits and a processor of superconducting qubits. The spin processor, called spin 2, still has a very limited number of qubits, so this only has 2 qubits. And the superconducting processor that we offer has 5 qubits currently, and we're upgrading it to 7 qubits and then more qubits after that. And all of these backends, the emulator backends and the hardware backends, can be found at quantuminspire.com. How do you work with Quantum Inspire? Well, first of all, you need to have an account on Quantum Inspire to be able to access the hardware backends. You can access the system without having an account, but then you're only able to use a small version of our emulator for testing and testing purposes. Normally, if you go to the web front end, you log in with your own credentials, and you can create an account there using your own email address, etc. But for this hackathon, we already made sure that everybody has an account and a password. So if everything went well, you have your account and you can log into to Quantum Inspire. If something doesn't work, please contact us through the correct Slack channels. If you want to use the SDK to do some more advanced programming, the best thing is to use your API token, and you can find it on the website by going to your account, and there you'll find your API token somewhere here at the bottom, and you can copy it and you can use it locally, and that facilitates the access if you use an SDK or do programming directly through our API. Talking about our API, we offer an SDK. The SDK is actually very slim SDK. It's mainly a translator between OpenQuasm of IBM and Project Q that was once developed by ETH in Zurich, and it translates those languages to our language, Quasm, and translates the results back. So you can use our own language, Quasm, but you can also use OpenQuasm from IBM to do programming, and you can use also Qiskit to develop more sophisticated programs, for instance, using their libraries and their components and utilities. And you will find Quantum Inspire as one of the backends in Qiskit as a third-party provider. But you can also directly program Quantum Inspire either through the web interface or through the SDK. I'll show you a little bit how that works in a few minutes. But basically, we have a language called Quasm. There's some more information on our knowledge base about Quasm. You always have to start with these two lines. Version 1.1, that's the version number of Quasm that we use. If you get this one, nothing will run. And you always have to specify the numbers of qubits that you're using in your program. It can be 2 qubits, 1 qubit, 20 qubits. But of course, the number should fit the number of qubits in the backends that we have. For the hardware backends, the number must be very specific. So if you use spin 2 as a backend, you need to state here qubits 2 because we have 2 qubits. Even qubits 1 will not work. If you use our superconducting system, which has 5 qubits, you have to specify qubits 5, which means 5 qubits. If you use the emulator, which can emulate anything between 0 and 34 qubits, you can specify any number, of course, and that will automatically pick the right number of qubits. And here you see a little example of a very small part of a program. You have these standard gates like X gate, Hadamard gate, and all kinds of single gates, which you can find also more information here. Multi-qubit gates and some different ways of different languages, language syntaxes that you can use, like denominating a parallel operation. So in here, an X gate and Hadamard gate are done in parallel. But in practice, the compiler of the hardware backends will determine how these gates will be done, whether they will actually be done in parallel or sequentially. That depends on the functionality that's offered by the backends. Some more about the hardware specifics. You can measure no qubit at all. If you specify that you don't measure a qubit at all, then by default, the system will always measure all qubits because it's not really relevant to measure 0 qubits. But you can also specify to measure all qubits or to measure only a part of the qubits. For instance, suppose you have a 3-qubit algorithm like this, and you measure only the first qubit, then you would have to add a measure statement here at the end. And in that case, It doesn't matter what the outcome is of the other qubits, because in practice they will all be measured, but the measurement results will be binned in such a way that you will see only the results for each qubit. So if a qubit at the end of your measurement, and you do not measure the qubit like qubit 1, it doesn't matter which state it is, the state that is registered will always be a 0. That's called binning, and you'll find some more information about binning on our website as well. I already talked a little bit about the circuit depth with the numbers of qubits. One other thing that you have to take care of is the number of shots. If you use hardware backends, you'll find on our website how many shots you can run your algorithm. This differs between the different backends, so it's maximized for the different backends and depends on the memory limitations of our hardware. But there's something very special when you run it on an emulator, and I'll talk a little bit more about that. But always define a good high enough number of shots on our hardware backends in order to get good results. Something more on an emulator. You can find our emulator, which is called the QX emulator, also on GitHub. On GitHub, you'll also find a compiler, OpenQL, that is written by QuTech, that you can also use together with the SDK or to compile programs in any way you want. Anyhow, if you don't use OpenQL, the backends will automatically decompose your algorithm into a certain set of native gates that our backends can handle. If you want to do more sophisticated decomposition, you could use OpenQL. And here you can also find some more in-depth knowledge about the language that we use, libcasm, and also parse it to parse those files if you would want to go that way. And some more emulator specifics can be found on our knowledge base, and then especially about the optimization of simulations. And I'll explain this a little bit more by looking at these two algorithms, these two circuits. Let's look at this first circuit where we generate a Bell state using a Hadamard gate and a CNOT. On an emulator, the exact state is known at the end of this circuit. So when you use our emulator, and I would really advise to use our emulators first to try out your algorithms and then later run it on our hardware backends. But if you use our emulator, usually you don't have to specify a measure statement at the end. And it's actually recommended to not specify a measure statement. If you do not specify a measure statement, then this circuit will be executed only once. And the exact probability amplitudes for all of the possible output states will be returned to you as a user. If you do specify a measure statement at the end, like here where we add a measure Z at the end, then just like here, you have to specify the number of shots that you want this circuit to be executed. But these number of shots will actually be executed on the emulator. So if you specify 1,000 shots or 10,000 shots, the execution of your algorithm will last 1,000 times or 10,000 times longer than when you don't add a measure statement at the end. So in general, when you use our emulator, don't use measure statements at the end. And I can't repeat this enough. If you do it, don't use measure statements at the end. If you want to measure in a different basis at the end, you can pre-rotate the states here at the end in such a way that the measure at the end, which will always be done in the Z status, is then done in a different basis. On the hardware backends, that's also a little bit different. You can specify different bases to measure your algorithm in. I understand that it might be difficult to understand all in such a short time. So please go to our website, go to this site, optimization of simulations, and there you'll find lots of information on what this actually means in practice, but also some differences between how to program this when you use either the web interface, Qiskit, or Project Q, because there are some minor differences between using all of those languages when you want to do optimization of simulations. So again, this one is very specific, very important to read. In a few minutes, we'll go over to my next colleague, Tumi, but I want to quickly show you a website and some specifics on our website. So if you go to quantuminspire.com, you'll find our website. Here you can log into your own environment where you can look at your results of your algorithm if you don't use an SDK. Here's the knowledge base, and I'll quickly go there. So the knowledge base gives you all kinds of information. If you're new into quantum computing, you can find here a basic introduction about quantum computing. There's a quick guide for basic users that tells you a little bit how to work with our editor, how to execute algorithms, how to create a new project, etc., etc. It tells you also a little bit about how the qubit register is used, and also how results are stored in a binary register. So make sure that you read this if you're new to quantum programming. Then there's an advanced user guide, which goes into a little bit more detail about the SDK. And here you will also find some more specific things about our language, like specific qubit gate operations or single gate multiple qubits language phrasing that you can use. And here you also find at the emulator topics, here's the section on optimization of simulations. And like I said, it's quite a list. But it's really important that you go through this in more detail if you don't want to spend too much time waiting on the execution of your algorithms. This is how the environment looks like when you log into your system and you use the web interface to program your languages. Here you have the editor. You can type in all kinds of commands here to do operations on the qubits, like you do an X gate or an Hadamard gate or whatever. So let's do a Hadamard gate here. This puts the system into a superposition, and we do a Z measurement at the end. Here you can select the different backends where you want to execute your algorithm. So you can execute on Spin2, on Starman 5, or on one of our emulators. And this emulator is out of use. This is a HPC system that is no longer used by us. We now have a new HPC system, so you can use this one if you want to use a large number of qubits. You can use this one if you want to simulate only a small number of qubits. But let's use Spin2. If you want to run the algorithm, click on Run. Give your experiment a name, like, sorry, my typing is a bit slow. You specify the number of shots, and you click on Run. And meanwhile, while it's running, so here you see the results, and here you see a pending job. So this one is now running. You could also change this and, for instance, measure in the Y direction. Run it again. Specify the number of shots. I'll leave it this time. And here you can look at your results. Here's the experiment that we just did. It's already finished. The other one is scheduled to be run. So like, look at this. We would expect a 50-50 distribution between the 0 state and the 1 state. You see that's not perfect. And especially I have to warn you for Spin2. Spin2 is a very new technology. It's not that far developed as superconducting qubits. So the fidelity is much lower. So in general, when you use Spin2, you'll find much lower fidelities than when you use another backend. So I can even run this. Oh, sorry. Go to the project, results. The other one is now running. Let's give it 1 more minute. That's also done. So here you also see a superposition if you measure in the Y basis instead of not measuring the X basis, which would give a different result. But if you measure in the Y basis, then you also get a 50-50 result on this backend. This is all I have to say in this short time. If there are any questions, please, I've 1 minute, I think, to answer some of those questions.
Yeah, let me really quickly ask you one of the questions. So Kai_Bud has asked, in image processing, binning usually means reading multiple pixels as one pixel to quickly get a rough image result before focusing on one region. Does binning have a similar concept in Quantum Inspire?
A little bit. I think it's, if I hear it like this, it's a little bit different. Suppose you have two states. Let me see, I try to give a good example. So if you have 2 qubits, then you have a 0,0 state, a 0,1 state, a 1,0 state, and a 1,1 state as probable output states for such a system. If you measure only 1 qubit, let's say qubit 0, then for instance, the 0,1 and 1,1 state are not really relevant. So they will be put into one state, and that's what we call binning here. Not sure if this is completely clear, but it does mean that you put all the results that are for the qubit states that are not relevant all on one big pile or in one bin, output bin.
Well, thanks so much, Richard, for the talk and for answering that question. And now we can move on to the next mini talk by Tumi.
All right. Hi, I'm Tumi, and I'm here to continue our presentation. So let me just share my screen. There we go. So Richard already explained in detail about the Quantum Inspire interface. However, I'm going to take a step back and explain a bit more about why these quantum computers are useful and some basic quantum mechanics that will probably come in useful for the project, for the challenges that will be happening tomorrow. So starting from the top, there's two useful behaviors of quantum bits that are what make them so interesting for us to use. The first of these is superposition. Like all of you have used a computer before, so that means that you probably know what bits are. And bits are essentially states, 1 or 0 states that are used to store data and to do operations on the computer. Now, when we go to a quantum computer, these bits get replaced with quantum bits, and these quantum bits can enter superposition, which means that they can be both in a 1 and a 0 state at the same time. Now, what that means in practice is that a quantum bit that is in perfect superposition will have a 50 chance of being measured out as a 0 state or being measured out as a 1 state. And this 50-50 probability is not a necessity, as depending on the state of superposition, this probability can shift to, for example, 70-30 or any other probability distribution in between. Now, on its own, this is not very interesting, but we combine it with another effect, which is called entanglement. And entanglement is that when you entangle 2 qubits to each other, the measurement results of 1 qubit, well, the qubits both share states. And if you know the states, you can fix the state of the second qubit by measuring the first qubit or vice versa. For example, if I entangle 2 qubits and have an entanglement of a 0-1 state, it means that when I measure the first qubit and find it is in 0, then I know 100% sure that the second qubit will be in the 1 state. And what's so interesting about this entanglement phenomena is that you can take your 2 qubits, entangle them, and put a whole lot of distance between them, and it'll work. You can take qubit 1, put it on Mars, and take qubit 2, put it on Jupiter, and as long as your state is stable, they'll still be entangled. So if you measure qubit 1, you'll get your 0 result, and you can know for sure that somewhere at the other side of the universe, your entangled qubit is now in state 1. Now, what's more interesting is that when we combine these two effects, we can do some interesting things. So let's say we have 2 entangled qubits, and we put them in a superposition state, so that the superposition is a superposition of a 50% chance of being in the 0-0 state and a 50% chance of being in the 1-1 state. if we measure this entangled states and we see that our qubit 1 has 0 results, we know with full certainty that our qubit 2, no matter where it is in the universe, as long as the entanglement is still intact, will also be in that 0 state. And vice versa for if you measure a 1 state. Now, the explanations I gave before were a little bit simplified, as superposition is much better represented in a form known as the block sphere. Now, what the block sphere is that instead of saying that your superposition state has a certain percentage of chance of being in state 0 and 1, you instead represent your state as a vector that is pointing at the surface of the sphere. For example, if our qubit is in the 0 state, we have an arrow pointing directly up at the 0 state. And if we measure this out, we'll have a 100% chance of measuring 0. Same goes for the opposite. If our qubit state is pointing downwards at the 1 state, then our qubit will have a 100% chance of being measured as a 1. However, this is where it becomes fun. If we put our qubits in a superposition state, so somewhere in the middle, for example, let's point at the x-axis, we get our 50% chance to be in state 1 and a 50% chance to be in state 0 when measured out. And all the in-between values will have the other probabilities of 80%, 30%, or anything else. Now, another assumption I made in the example is that we are always looking at the value of the qubits in the z direction, but there's no actual necessity for that to be the case. We can very well just look at the state of the qubit in the x direction, in which case our superposition state that was pointing the x-axis no longer becomes a 50-50, but now has a 100% chance of being the 0 equivalent on the x-axis, or in the opposite case, a 100% chance of being the 1 position on the x-axis. So depending on what direction you measure your qubits, the states that were in superposition can become guaranteed states, or vice versa. And this is a very useful property to make use of. For example, to give a practical example, we can make use of this for a certain form of quantum encryption. Now, let's give an example. Let's say we have Alice, who for some reason has access to a quantum device, but we shall not think too deeply about that. And Alice measures her qubits in the Z basis. And as measurement results, she happens to find out that her qubit is in the 1 state. Now Alice hands her qubit over to Bob, who for some reason that is not disclosed has access to a quantum measurement device. And then Bob does another measurement in the Z basis. Because Alice and Bob measured in the same basis, Bob's results will be the same results as Alice's. Like the qubit was in the 1 state, was pointing up, and it's still pointing up when Bob is measuring it. So if they measure in the same basis, then nothing strange happens. But now let's say Bob measures the qubit in the X basis. Now, as you remember from the picture of the block sphere, the X basis equivalent of the 1 state is now a 50-50 position, meaning that Bob will now have to deal with the fact that his qubits can 50-50 give him a 0 or a 1. And for notation reasons, when we talk about measurements in the X basis, it's helpful for us to call the X basis 0 state the plus state, and the X basis 1 state the minus states, but they mean the same thing. Now, this also holds for the opposite case. Let's say Alice takes her random qubits, measures in the X basis, and now she gets a measurement result a minus states. Now, if Bob measures in the Z basis, this will mean that he has a 50-50 chance of getting either 0 or 1, or if he measures in the X basis, he will have a 100% chance of measuring the same result Alice did. So from this, we can make the following conclusions. If Alice and Bob measure in the same basis, measure the same qubit in the same basis, they will always get the same results. However, if they measure in different bases, Bob has a 50% chance of getting a different result. As the basis that Bob is measuring in, as in the basis that Bob is measuring in, the state that Alice measured will now be a superposition state, and then you're tossing a coin. So what you could conclude is that by telling each other what basis they measured in, let's say Alice and Bob measured in random bases. So first they both measured in the same basis, then they measured in the different bases, and then they measured in the same basis again. They can essentially convey information. For example, if Alice measured one first in the first round, Bob also would have measured one. If they measured something else in the second round, then that's too bad. If they measure in different bases in the second round, it's too bad, so we ignore that. But if they measure in the same basis in the third round, then they can know for sure that they have the same value. So by communicating what basis they've measured, they can essentially convey the states, or they can convey information in a way that they do not explicitly have to say what the contents of that information is. And this is why it's useful to make use of this as a form of encryption. Because, as you know, encryption essentially requires two parties to be able to share a key in such a way that no third party can know what a key is. Now, we can take it even further. Now, let's say there's an eavesdropper called Eve that manages to steal Bob's qubits and wants to break the key that Alice and Bob are generating. So Alice measures her qubit in the Z basis. She gets, as a result, a 0. Then, who has no idea what basis Alice measured the qubit in, also by sheer luck, measures the qubit in the Z basis, and she gets a 0. Now, Bob does a Z basis measurement, and he gets a 0, and he doesn't suspect a thing, but he now knows the value of their shared key because she also has access to the qubit. However, this situation assumes that Eve had a bit of luck, because with the same probability, Eve could have decided that, okay, now let me just measure in the X basis, because I do not know what basis Alice is measuring in, and she's probably measuring at random. And then suddenly something changes. By measuring in a different basis, Alice has now modified the state of the qubits and now has a 50% chance of getting a result in the plus state, or a 50% chance of getting a result in the minus state. And now if Bob, still measuring the Z basis, reads his measurement outputs, there's now a 50% chance that he and Alice have a different result. So let's say Alice calls Bob and says, hey, I measured this qubit in the Z basis. Did you also measure it in the Z basis? And Bob says yes. And then Alice now says that her measurement result was a 0, and Bob notices that his measurement result is a 1. Bob can know that somewhere something fishy happened in between him and Alice, and that they should probably abort the operation. So, to draw conclusions, even if it manages to intercept qubits, there's a 50% chance that she will measure in the wrong basis. Of course, this is assuming that Alice does properly randomly choose the bases that she measures in, which will then result in Bob having a 50% chance of getting a different measurement result than Alice. So by repeating this experiment a bunch of times, let's say 100 times, we could now use a subset of these results, just sacrifice them, by having Alice tell Bob that for measurements 40, 50, and 60, she got the value 1. If Bob has a different value for this measurement, then that means that somewhere, assuming that these measurements are in the same basis, if Bob has a different value for these measurements, it means that somewhere something changed the states, and there's probably an eavesdropper that has managed to get their hands on the qubits. Of course, this is not without any flaws, because if Eve manages to intercept both their phone call, so when Alice says that, hey, I measured in basis X for this qubits, you should measure in that basis as well, and also have access to the qubits, then, well, there's nothing to be done. But I think at that point, you probably have bigger things to be worried about. Now, this is a very simple example of actually physically passing on a qubit between two parties. But by making use of entanglement, you can make this setup a lot more practical, because if with proper equipment, you can remotely entangle two qubits, meaning that you don't need to constantly be sending qubits back and forth, but you can just generate an entanglement state and do a similar setup to this, where Alice and Bob hold onto their own qubits and instead use entanglement in order to get the key generation to work. In any case, I hope that this short explanation made things clear. And if there's any questions or any things that you're still worried, any things that you're still curious about, please feel free to ask these questions over the course of the next 2 days or today after the presentation. So if there's any questions from the Twitch chats.
Yeah, we can
I think I still
definitely
have
bring up one of the questions. One of the questions is, how can we find the error rates of the quantum hardware that Quantum Inspire puts up? And kind of to build on that, how do these error rates affect, an experimental implementation of this protocol that you talked about?
The error rates, well, first of all, you can pretty easily find what degree of error we have by just running a quick experiment, like the way that Richard did so. Like if you do an experiment where you do a measurement at the end of the circuit, what happens is that the system does a whole bunch of measurements, and then you can see, for example, if you have a situation where the results should be 50-50, but you have results of 40%, 60%, then you know that there's around the 10%. There's around this 10% shift in your fidelity. Although I think that the Quantum Inspire site should have a page that has the different error rates and different benchmarks of the different devices.
Yeah, maybe I can quickly add to that. Indeed, we have fact sheets on our website. If you go to our website and go to our landing page, there you find part on with specifics of our hardware backends. You also find on a knowledge base, and there you can find detailed single qubit gate fidelities and 2 qubit gate fidelities, readout fidelities for the hardware backends.
Yeah. As for your second point, yes, that is actually a good point, because you could end up doing everything right, and there was no eavesdropper, but because of the fact that the qubit systems are not perfect, you might get the opposite result. So Bob and Alice measure in the same basis, and they get different results. But in order to avoid that from being a problem, it's very important to have a large enough. It's important to repeat the experiment enough times so that you can build some redundancy in your shared key and in your shared results. So there's a lot of theory and a lot of experimentation that's been done on that. So this is still the simple case. There are more advanced cases that will make the error rates of the system less of an issue. But more on that later.
Absolutely. Thank you so much for such a fantastic talk to me and answering some of the questions. Miguel, I believe you're next. So feel free to start sharing your screen and take it away.
Absolutely. Let me try to do that. So hopefully you see my screen by now. Good morning, afternoon, or good night, depending on where you're joining us from. My name is Miguel, and I'm a research engineer at QuTech, where I work with superconducting systems. Now, on their previous presentations, my colleagues have already discussed how to use the Quantum Inspire platform and some concepts for quantum information science. In this part of the presentation, I would like to build on these concepts and explore with you some of the challenges that we are working on at QuTech. With this, I hope to motivate you in potentially pursuing some of these topics for your project here at iQuHACK. But I also hope to show you how these challenges we're working towards have influenced the architecture of the quantum systems that will be available to you for programming during this hackathon. So in this presentation, I'll start with a brief introduction to quantum error correction, for those of you who are not familiar with the concept. I will take this opportunity to briefly highlight some recent work done at QuTech on this topic exactly, quantum error correction, in a system that is incidentally very similar to the one that will be available to you during the hackathon. I will then give you a brief overview of Starman 5, one of the hardware backends of Quantum Inspire, and one of the ones that will be available to you. Finally, I'll give you some tips on the best ways to use the systems provided by QuTech in an attempt to spare you from some of the most common mistakes we've found among users. Overall, I hope this talk contributes to your ability to explore, implement, and analyze these systems over the next couple of days. So without further ado, let me start. So as you might know, quantum computers nowadays tend to be very error prone. One potential solution to this involves error correction, of course. In a classical computer, error correction employs redundancy to protect the information that is stored. However, in quantum information theory, the no cloning theory prevents the copying of information, making quantum error correction harder to implement. However, this is still possible to guard from errors by instead spreading information of one qubit onto a highly entangled state of several physical qubits. Now, doing so allows us to perform multi-qubit measurements that do not disturb the quantum information encoded, but that still discretize, project, and potentially allow the identification of errors that have occurred, therefore allowing their correction. It is most important to note that this can happen without compromising the degree of freedom that now encompasses the logical qubit. So I wanted to clarify everything I just told you with an example in which I will focus on the surface code, a particular quantum error correction code that has achieved prominence due to its low error threshold and moderate hardware requirements of nearest neighbor couplings. You can see the example of a set of qubits here, organized in a very particular manner, the reason for which will become apparent to you soon. Now, the goal of quantum error correction is to encode information redundantly in such a way that errors are discretized, signaled, and could be corrected. Like I said previously, we do this by preparing a highly entangled set of states, which I've described here. And we do this across the qubits that have been labeled from 1 to 4 as data qubits. And this will constitute our logical qubit state, a state that is protected from a set of errors. You can see that due to the way in which these states have been chosen, since no single qubit error on a physical qubit, again, these are qubits D1 to D4 that we have described here, no single error on a physical qubit could lead to a logical qubit error, which means, for example, transforming the logical 0 into the logical 1 that would constitute a logical error. Now, you may ask how we can detect these errors during execution, and we do so by measuring what we call the code's stabilizers. These are operators that map the parity of this highly entangled state onto auxiliary qubits, which we have described here as NCOS from A to A1 to 3. In this particular code, there are two types of NCOS, X-type NCOS and Z-type NCOS. And although these do not disturb the logical state of the qubit, you can see that by showing how these stabilizers sets how the stabilizer sets actually commute with the logical states. But they do project and discretize single qubit errors that happen. Furthermore, since stabilizers anti-commute with errors, they're able to signal these to the user, allowing for their potential correction. Now, the example I presented here is a fairly limited version of quantum error correction, which we call a distance 2 surface code. Due to its limited size, you can only detect up to 1 error. Now, you can see this fairly easily by looking at the logical states that I've written. 2 errors, for example, on the 2nd and the 4th qubit would lead to the logical 0 state transforming into the logical 1, which would cause a logical error. Now, larger versions of this code do not suffer from this problem, but these are out of scope for the purpose of this presentation. Now, the last important part is for me to really convince you of these highly entangled multi-qubit states, for me to convince you that they really form a logical qubit. Now, if that were the case, one should be able to perform operations on the logical qubit. And indeed, this is possible. By performing multiple single qubit operations on the physical data qubits, you can see that, for example, by performing multiple individual operations, you can combine them into a logical operation. So for example, Z operations on the first and third qubits in this example would change state 0 into state 1. And therefore, we can control this logical qubit just like any other qubit. Now, having gone through this sort of very theoretical part of the presentation, I wanted to introduce you to the Starman 5 system. This is a superconducting quantum processor that was fabricated with the specific goal of implementing the Surface 7 code, and that is now available to you through Quantum Inspire. Now, let me start by saying that most of what I will talk about today regarding Starman 5 and a lot more that I won't be able to cover is available online. Indeed, from the Quantum Inspire homepage, you can easily find your way to the hardware backends landing page, which I'm showing here to the left. You can then, from here, select one of the two hardware backend types, Spin 2 or Starman 5. And this will take you to a web page with most information about the system that is required to run algorithms. However, for more interested readers and users, you can also download a fact sheet, and this will contain really all technical information about the device, the system, and how one can program and use it. Now, finally, for code examples, more background, and even an historical perspective on quantum computing, excuse me, you have the knowledge base, which is all of this available to users on the top of all Quantum Inspire website pages, and is therefore at your disposal. Right, so regarding Starman 5 specifically, from the image on the right, which shows you the superconducting quantum processor, you can probably already see that this was purposely fabricated to accommodate a Surface 7 code, like the one I previously described. Now, unfortunately, 2 of its qubits won't be available for you to use through Quantum Inspire, and so the system will effectively have 5 qubits that can be controlled. For the electrical engineers and experimentalists among you, qubit readout is implemented through 2 feed lines in the frequency multiplex scheme with filtering to mitigate Purcell effect. Initialization, which I will soon show you how to use in programs. Initialization is done by post-selection in order to maximize its fidelity. Single qubit gates are achieved in 20 nanoseconds and 2 qubit gates in 40 nanoseconds using the sudden net zero scheme, something we've recently published, and to which I review here a reference at the end in case you are interested to read more about. Now, performance metrics for this system are available here, although they could have changed slightly when you get to the system, since it is automatically calibrated periodically. Now, for the Starman 5 system in particular, I should add, I think this was a question that was presented before, all these metrics are constantly available and updated on the web interface, the graphic user interface, which communicates directly with the system. So the most up-to-date metrics you will always be able to find in Quantum Inspire's web interface online. All right, so in the last part of this presentation, I wanted to give you a few tips on the best ways to use the systems provided by the QuTech to fulfill some of the challenges that will be announced tomorrow. Now, these arose from a selection of common mistakes we found when talking to users, and hopefully this way we can spare you some headaches. So let's see, the first word of caution is directed at the fact that Quantum Inspire doesn't yet allow repeated measurements, although interestingly, this may become available very soon. Therefore, although the graphic user interface will correctly interpret programs with multiple measurements, even rendering, like you see here, an illustration of, any program that is submitted with multiple measurements to Starman 5 or any other system will be truncated for correctness. And what this means is that anything after the first measurement state, the first measurement instruction will be effectively ignored. Users should be careful when writing their programs to account for this. As for example, here, none of what is shown in red would actually be executed in the end. Now, a common mistake we have is for people to write multiple measurement instructions in sequence when trying to build a multi-qubit measurement. Indeed, this will not work, as instructions after the first measurement will be truncated. Instead, users should use an explicit multi-qubit measurement statement, of which we have two kinds that I show here on the right. Now, another common question we have relates to qubit initialization. Although we provide explicit instructions to achieve this, if a user doesn't explicitly initialize these qubits in the beginning of a program, they will be automatically initialized for him in the 0 state. All right. Another thing I wanted to bring to your attention is the native gate set that is available to our quantum processor. Indeed, only a subset of the operations that are allowed in Quantum Inspire generally are natively supported in Starman 5. Others, although allowed, are decomposed into this native gate set automatically. Now, you're very much free to use this functionality, but you should be aware of the fact that non-native operations will suffer a slight performance penalty, which could be particularly relevant if you're trying to assess the fidelity or to study the fidelity of your circuits. So indeed, the native gate set in Starman 5 consists of 3 single qubit gates: the idling gate, this is a trivial gate whose importance will become apparent soon, the arbitrary rotation around the x-axis, and arbitrary rotation around the y-axis. Now, the 2 qubit gate supported natively is the CZ gate, which I show here. Furthermore, we have native support for initialization to the 0 state and measurements in the Z basis. However, we do support a lot more commonly used gates through the composition. So things like the Z, Hadamard, T-dagger, S, and S-dagger gates are all available for use. For example, the Hadamard gate here is shown to be implemented through a decomposition to 2 single qubit rotations. Although you don't need to program this in yourself if you want to make use of the operation, you should expect slightly lower fidelities and take that into account. So let's see, what is similarly true for the CNOT and the swap instructions that are supported by the platform and which are implemented through single qubit rotations and several native 2 qubit gates, which here is the CZ gate. Right, to close this topic, we also provide initialization and measurement in different bases, which in all cases is accomplished by pre-rotations that map operations from the Z basis onto whichever basis is required by users. All right, a final word of caution relates to scheduling of user programs. So indeed, all programs that are sent, that means run through Quantum Inspire and Starman 5 in particular, are precompiled and scheduled according to an ALAP strategy. That means an as late as possible strategy. What this means is that every instruction will be placed as close as possible to the end of the program, which in most cases means closer to the final measurement. Now, we do this in an attempt to conserve one of the most important resources in a quantum computer nowadays, which is the coherence time of qubits. However, if you're not aware of it, you may fall victim to it, especially in case you're running very scheduling sensitive programs, like those with echo pulses in the beginning of a circuit, for example, or in the middle of a circuit, I should say. In those cases, users should use the idling operation that I've mentioned before to control the scheduling of instructions. And I'm demonstrating here a very simple case where we do an echo pulse on qubit 2, and we use the identity gates to ensure that it is scheduled exactly at the middle of the sequence of gates applied to qubit 1. So to conclude, I wanted to summarize the contents of my presentation here today. I started by giving you some background on quantum error correction and motivated how important an avenue of research it is and how likely it will continue to be in the future. Then I presented Starman 5, a processor that was built with the exact purpose of QEC at heart, and that is now available to you through Quantum Inspire for your use in whichever projects and programs you see fit. And finally, I give you some tips that could be useful in your work over the next couple of days and the challenges that will be announced soon. I hope you take this opportunity to explore quantum computing on the superconducting quantum processor, implement NISQ algorithms, and may I suggest even potentially explore the error channels that are inherent to NISQ hardware. And most of all, I hope everyone has a lot of fun doing so. So with this, I wanted to thank you all for your attention, and maybe we have a couple of minutes at the end for some questions.
Thank you so much for a wonderful talk, Miguel. There are some questions, so I can start by asking, is the RY gate or rotation gate in general implemented in software by changing the reference?
That is a great question. And in this case, the answer is no. It is parameterized. So the rotation angle of the RY gate is parameterized in amplitude directly in hardware. And so it is not implemented in software. That was a very short answer.
Yeah, no, it's a direct answer. And another question is, what are some of the main experimental bottlenecks to scaling up surface code experimental implementations?
Oh, wow, that is indeed a very interesting question. So a lot of factors play a role, as with any real world system. It tends to be that fabrication variability, in particular, has had a considerable impact in our ability to manufacture these processors, making sure they meet strict design requirements that allow us to implement protocols that are otherwise very sensitive to correlated errors, like, for example, quantum error correction. Now, that's a challenge we face sort of in the near future. If one looks years ahead, then one might start to identify other challenges when it comes to scaling up the technology, either through interfaces, control, electronics, or probably more important for experimentalists and physicists, the coherence time of qubits, which will have a direct impact on the fidelity that is achievable with these chips. Now, it's a very complex question to answer, but I hope I did it some justice.
Absolutely, I think you definitely did, and thank you so much again to Richard and to me and Miguel for 3 fantastic talks. We will, if you all have any other comments, please feel free to go ahead. But thanks so much to QuTech creating the quantum future. I've seen the challenges, and I can let you all know that it's going to be a very exciting 26 hours starting Saturday.
We certainly hope so.
Yep.
We'll do our best to support participants in whichever way is easiest. You'll certainly be able to reach us through Slack throughout the 2 days of the competition.
Right. Yeah, so we'll end it there. Thank you so much, everyone. And the next talk will be a tutorial by Microsoft and IonQ. And so stay tuned on this Twitch. Yeah, see y'all.
Thank
Bye.
you.
Thank you. Yeah.
Thank you very much.